e-learning program, February 2021. Thank you for joining us. I hope you all are keeping well. I am Jannat Ara Tahamina, studying in medical physics in Bangladesh and working at the South Asia Center for Medical Physics and Cancer Research, SCMPCR. I am with you as a moderator of today's program. At the beginning of today's session, I inform you that we have changed the schedule of the next lecture, Brachytherapy, QA and Safety, on 20th February, and group discussion on 21st February. The lecture will be held at 10 a.m. to 11.
Sorry, Jannat, please try to reconnect. We are not hearing you. Gerald, sorry for the disturbance. We'll get back to you soon.
Sorry, there was a problem. Can you hear now?
Yes, we can hear you.
Yes, please.
Okay. Today, our honorable speaker is Dr. Georg Schwickert, Manager Application Specialist at Varian Medical Systems. He also works as an Application Support Specialist at Brachytherapy at Varian Medical Systems, Germany, and European Brachytherapy Sales Specialist at MES Nordion, Haan GmbH. He has 25 years of professional experience. Today, we have our another speaker, Dr. Hensley also. We will deliver a small theoretical lecture in between the practical session. It is pleased to inform you this program has been accredited by International Organization for Medical Physics as CPT event for medical physicists with 22 CPT credit points. This is to inform you that there will be an examination at the end of 8 lectures with practical session and group discussion. You have must pass the examination for certificates with CPT points. Otherwise, you will get attendance certificates only. Before start, I remind you that your question or any comment, type in the chat box. We'll pick up your questions after the lecture. And kindly mute your microphone and stop your webcam. Okay, today's practical session is on transition from traditional treatment of cervical cancer to conformal adaptation using modern target definition. Now I invite Dr. Georg Schwickert to deliver your talk. Are you ready, sir?
Yes, I'm ready. Thank you, Jannat, for the introduction.
Now platform is yours, sir.
Thank you. So good evening, everybody. I hope you are still well and healthy in these difficult times. Today I want to talk about the Manchester dosimetry system and how we create plans, standard plans, which means intracavitary plans, and how we can move to the more image-based planning or adaptive planning for cervical cancer. And here are my topics. So I just want to start and explain again the Manchester dosimetry points A and B. You heard about that already last week, but I want to go a little bit more into details here. And then I want to show you the reporting points and volumes. This is based on our ICRU 89 report, which I would highly recommend for you to read. It's about 250 pages, but it's really worth to read. And I would say when you read this, you know everything that you need to know about brachytherapy of cervical cancer. Then I want to speak a little bit about applicator selection. So you can use different types of applicators for this treatment. I will present, of course, the Varian applicators, but I think that is vendor independent. Other companies have the similar applicator types. And then the main part of today's presentation is I want to demonstrate Brachyvision as a planning system. So I will develop a plan, intracavitary plan, and then we go to the more advanced interstitial plan, and you will see the differences, and you see how this could be of benefit for the patient. If there's some time left, I will talk about ring applicator commissioning. This is a common problem for all vendors, that the positions inside the ring channel are not exactly at the same positions where they are in the planning system. But there is a possibility to solve this problem, and that is something that I want to show. And last but not least, just a few words about image fusion. If you intend to do plan summation between external beam and brachytherapy, it's good to know some aspects of this. So Manchester points A and B. First, I want to talk a little bit about the basic anatomy. So here you see the uterus, you see the corpus, you see the cervix with the external cervical os. This is very important for the point A definition. You see the fornices here, which is the, let's say, left and right upper edge of the vagina. There we will place the applicator, and that's also very important for point A definition. And this is the vagina, and here we assume the tumor. Of course, depending on the stage, it could grow into the vagina, or it can extend along the parametrium to the pelvis wall. So this is very much dependent on the tumor staging. How do we treat this? We use different kind of applicators, as I already mentioned. One possibility is to use 3-channel applicators. This is a typical application with a Manchester applicator or a Fletcher applicator. So you have ovoids where you have source positions, and you have the intrauterine probe, which is called tandem, where you have the source positions, and we want to achieve a dose distribution that covers, of course, the cervical area here. Alternatively, you can also use a ring applicator. Ring applicator is an applicator that consists of 2 channels. So you have the tandem, and you have a ring channel, and you have the source positions inside this ring channel. Here again, the anatomy, and here the definition of point A, point B. You have seen that already last week. So this is a very old system. So the authors or inventors, Todd and Meredith, they published this first in 1938. And actually, they were looking for points to describe the dose distribution, which are good points in the anatomy, which we can rely on, that we have a very robust point for the dose prescription. And if you place points close to the tandem or close to the ovoids, then you are in a high dose gradient region. And that is something that we want to avoid, because this would be then very much applicator and also patient dependent. And therefore, actually, they found out that this point A, how it's defined here, you have heard about that. It's 2 centimeters away from the mucous membrane of the fornices and 2 centimeters away from the center of the uterus channel. And this is a point which is quite robust related to the dose distribution, and it's considered as a control point. So it's not necessarily a point that we would specify as a target point, but more as a control point. Because if you normalize the dose to this point, you get a similar dose distribution for all your patients or all your treatment cases. And because of this reproducibility, it's a safe system. And the point A has slightly been modified in 1953, because on radiographs, it's not always easy to identify the fornices or to relate this to the top of the ovoid channels, or with a ring applicator, it would be the top of the ring channel or ring cap. So they changed this definition slightly, and they defined point A with respect to the last source inside the tandem. At that time, it was radium sources. And they were always assuming, okay, the last source in the tandem is at the same level as the ovoid caps, and which is also at the same level as the cervical os. And that is true for the previous Manchester applicators. They had a fixed geometry between ovoids and tandem. So this was always the same position. But with the newer developments of the Fletcher applicator years later, this applicator is more flexible. And if you have, let's say, the cervix more protruded into the vagina, then you can imagine that your ovoids come closer to point A. So they come more, or point A comes more in the high dose region. And that is something that you need to consider if you use this point A and point B dosimetry system. Point B is actually indicating the pelvic, or the region of the pelvic lymph nodes. In this region, you have the inner iliac lymph nodes and you have the obturator lymph nodes. And point A has also an anatomical representation, because as a control point, it's not only a point for a good minimum dose, but it's also a good point for a maximum dose, because you have some radiosensitive organs in the region of point A, which is actually the ureter and also the blood vessels for the uterus. So there is the uterine artery, and there's the corresponding vein also in close relationship to point A. A frequently asked question is, what is with point A when the probe is not exactly in the center of the uterus, but maybe tilted like shown here? Simple answer is that point A tilts with the probe. So we don't want to have point A in the high dose region. So we want to keep this distance, and so far point A moves with the applicator, with the intrauterine probe. Point B does not. Point B is far away from the high dose gradient, and therefore it stays where it is originally defined. Good. What is our goal? We want to get a pear-shaped isodose line, like shown here, which is normalized to 0.8, so that we can cover the treatment area sufficiently. And if you look if you look here on the FIGO staging, there's just shown FIGO 2A and FIGO 2B stage. And you see in 2A, the tumor is growing into the vagina. In 2B, it's growing along the parametria to the pelvis wall. So if you think of FIGO 2B, you can imagine that point A is really a target point in this case. But as I said, it's also a control point for the risk organs. And therefore, it's really a very, let's say, robust point regarding the dose distribution. There was a nice investigation from Dr. Wang from Taipei in Taiwan. He was investigating, is this anatomical point A, which is identified as the crossing point of the uterine artery and the ureter, if this point, anatomical point A, is the same as the Manchester planning point A. And what he found out is, so what he did is he marked these points with some clips intraoperatively. So that was a lymphadenectomy that he performed with 12 patients. And then he marked this point of the crossing point of uterine artery and the ureter. And he compared this with the planning point A. And what you see is that this does not match. So the planning point A is the inner points here, and this is the anatomic point A. And he found out that only 30% of the dose that, or 30 to 35% of the dose that is delivered to the Manchester point A is delivered to the anatomical point A. So there's quite a difference. So the question is Manchester point A still important? And there are some arguments against and some arguments that speaks in favor for using point A. And I just want to start with the pro arguments. So it's about 80 years old, even more than 80 years old, this Manchester dosimetry system. And we have very good experience, specifically with a local control of the tumor. It's a very robust point A, for treatment planning. We get the similar dose distribution in all cases. And it's a good point, as I mentioned before, to specify a tolerance dose, because it's not only target, it's also risk. What speaks against using point A? There is one point: if you perform the next fraction, you have your applicator always slightly different. So it's never exactly at the same position. So this point is not really reproducible. So you get more a region than an exact point. And then we've seen this in the slides before. Anatomical point A and planning point A do not match in general. And of course, what we are also missing is a biological target-based planning. However, if you look at ICRU report 89, there are two very important statements. And the first one is the dose at point A, despite all its limitations, represents the most widely used parameter in gynae brachytherapy worldwide. And in addition, the absorbed dose at point A is still the predominant method of absorbed dose prescription, regardless of the application technique used. So regardless what kind of applicator you are using, we want still to have this normalized to point A. Of course, it will change if we go into interstitial planning, then point A really loses the meaning. And we will see that if we go to this practical session and I show you how to plan with this. There was actually, with the last Astro-Gynae teaching course, there was a very interesting slide presented by Umesh Maheshwari from Mumbai. And he's asking, or he's comparing, how is the development? So he's asking the participant, or he asked the participant, who is doing MRI with the applicator in place. And you see how it developed in the last 10 years of this Astro course. So it's going up. So more and more people are using MRI imaging for this treatment planning. And on the other hand, he asked, okay, what do you use as a dose prescription? Are you using point A, or are you using the concept of high-risk CTV? And you see the tendency is also clear. Point A goes down, and the image-based planning methods go up. So it's quite interesting to see that development. Okay, some information about reporting points and volumes. This comes also mainly from the ICRU report 89. First of all, what is the target volume concept? There is the two volumes of interest. That is first the primary tumor volume, so the cross target volume or cross tumor volume, and there is the CTV. So the main focus on where we want to have a certain limit of the dose. And then it's separated into, or in three different volumes, in a high risk volume, in an intermediate risk volume, and in a low risk volume. And what is also important is the timing. So there's the time at diagnosis. There, the GTV, the initial GTV is contoured and evaluated. And then there is the time of brachytherapy, which is then the residual GTV. And during the course of external beam, the tumor shrinks roughly about 70% of the volume. So the area that you treat, or the residual GTV, is much smaller when you start with your brachytherapy scheme. And this is also shown here in this recommendation paper from the Czech Astro team. And you see the GTV here indicated, and you see the high-risk CTV with the red dots. So this is the residual tumor at the time of brachytherapy. This is the high-risk CTV, which always includes the whole cervix. And then we have the intermediate risk CTV here, which is basically a margin around the high-risk CTV. The margin is somewhere between 5 and 15 millimeter, but it does not extend to the bladder and rectum. So, and it contains also the, let's say, microscopic disease, or where there could be potential tumor cells. And then is a low-risk CTV defined, which also includes the whole parametria and also the whole uterus and the upper part of the vagina as well. Okay, in ICRU report 89, we have also reporting points and structures. And in this report, there is a separation between three levels. The first level is the minimum standard for reporting. And then the second one is the advanced level. And then there is a third level, which I don't want to mention here. It's more for research. So there is a lot of parameters that you would report if you go to level 3. But level 1, of course, most important, the minimum standard for reporting. First of all, you report the TRAC, the total reference air kerma, which is basically the product of treatment time and source strength. If you multiply that, you get the total reference air kerma. Then 0.8 dose, you should always report 0.8 dose. you should report the rectal reference point. This rectal reference point was defined in ICRU report 38. It's now called recto-vaginal point. The position has not changed. I think I have one slide that shows again the position. And then you should also report a maximum dose for bladder and rectum and the D2cc, so the 2 milliliter that gets the highest dose. And actually in this 2 milliliter is the lowest dose that we report. It looks like this here. So you see, first of all, you see here a bladder point, rectum point. Bladder point is defined on a plane which is perpendicular to the patient's axis, and you go through the middle of the bladder balloon, and then it's at the edge that is close to your applicator. And for the rectum point, you consider the, let's say, center of mass of your source positions. So in the middle of the sources in the vagina, you go perpendicular to the body axis again, and this rectum point is 5 millimeter behind the vaginal wall. So that's your rectum point. Both points are not necessarily the highest dose. So also the rectum point is not necessarily on the highest point inside the rectum or the rectum wall. You can see that here also on this slide. And you see the volumes here that we should report. So 0.1 cc is more or less the maximum dose that you get in this risk organs, and we should also report 2 cc as a more stable representation of the maximum dose in this organ. Good, this is level 2, advanced standard for reporting. It includes all reporting points of level 1, but it adds some more DVH parameters from the target. So D98%, D90, D98% has been introduced because it's a little bit more stable, because it's not at this steep gradient as the D90. And we report this for the high-risk CTV, for the intermediate-risk CTV, there is D98 and D90, and also for the GTV, and also for the pathological lymph nodes. And on the other side, the organ at risk, there's the bladder reference point that should be reported in addition to the rectum point. And then you see D0.1 cc and D2 cc for sigmoid and for the bowel. And there are some more parameters to report for the intermediate and low dose parameters for the bladder, rectum, sigmoid, and bowel, which you see here. Important again, I think that was also mentioned last week in the presentation. You should also report the vaginal dose points. I'll show you in a minute where these are, and the so-called BIPS points, which are in the middle of the vagina. So we are looking at this. I think Dr. Chameda has explained this last week. So we are here in a level of the uterine sources. And if you look at a ring applicator, you go just 5 millimeters from the ring cap in all directions, and you get your vaginal points that should be reported, or in case of a Fletcher applicator or Manchester applicator, it's very similar. You go just 5 millimeters away from the surface of the applicator. And this BIP points, important for external beam and also for brachy, are at the level BIP. You remember that posterior, interior border of the symphysis. And this is the first point, which is in the middle of the vagina, and we add another point plus 2 centimeter, minus 2 centimeter. And as mentioned before with point A, also the vagina is partly the target. So the upper part of the vagina is definitely a target, but the lower part of the vagina is a risk organ. So these points are important to evaluate the toxicity of the vagina, which hasn't played such a big role many years ago, but now it's getting more and more important also to report this point and points and look at the dose here. Good. That is basically the point where I want to switch over to Dr. Hensley. He wants to give you also some more information about Manchester dosimetry, and I'll just make him now the presenter.
All right, thank you very much. I believe my presentation is coming up, at least my slides are coming up. Share my screen. And happening. Yes, I think now you've got it, correct? Yeah. Okay. All right, hello everybody. I want to speak about a few more theoretical things, more about the concept. I will repeat a few of the things that Dr. Schwickert has just been telling you, maybe with other words, and maybe that is practical because I think it's very important that you understand the concepts behind the targets that are used and the way the procedure is done in gynecological brachytherapy. So hearing things twice with different words may be practical, I hope. Yes, here we are. Okay. You have just seen the definition of the Manchester point A. And for my part of the presentation, I want to use Manchester point A as a purely geometrical definition, purely related to the geometry of the applicator, and not look at the anatomical definition that we have heard about. So this is one way to look at this, and it's something that is actually very practical with the modern applicators that we have right now to see point A as a geometrical point. You have heard that this has been defined more or less as an average, and on this slide here you can see that for a large woman, point A may lie even inside the uterus, and for a small woman it may lie far outside. But this is a concept that has worked for very long, and the reason why this works is as Dr. Schwickert told you, that this is actually a kind of a control point, and it ensures that there is enough dose normally on the uterus, which is in here and where the tumor normally is, and still we keep the dose limited so that it does not produce any complications. That is the reason why point A has worked for many years, and it's actually still a good concept. But today we can do better because we can plan on CT or even on MR, and we can see the isodoses, we can see where the dose goes and which organs at risk are affected. And we can use tools like dose volume histograms to evaluate this, and then use dose volume histogram metrics like the V90 and the 90%, or the dose to 2 cubic centimeters on a risk organ to evaluate our dose distribution and to get a good imagination of how good the dose distribution is. So we could, in principle, continue without using point A, but I want to point out that in modern CT-based and MR-based planning, point A still remains important. And it remains important for an additional reason that I believe have not heard of before. At point A is a position where we should define a reference dose rate. Call this dose rate at point A 100%. Then you will have less dose rate out here, and you can define this on an initial dose distribution, which is the same for every application using this applicator. And you do this. I'll show this a little bit later once more, for standard loading of the applicator, and normally for equal dwell times or after a preliminary geometrical optimization. I will speak more about these topics in a few minutes. Okay, the problem with point A now is that if you would use point A as the dose dose prescription point for a large tumor extent, point A may lie too close to the uterus, and you would not get a coverage of this part of the tumor out here with the prescription dose. So what you might want to do is say, okay, then we'll put our reference dose out here, and then the dose will cover the complete tumor. But if you do this too early without fixing your reference dose rate here at A, what will happen is that you multiply everything, both doses and dose rates, with the same factor. So you increase your reference isodose, the red one, but you also increase the blue isodose shown here for the hot regions, what you might call the hyperdose sleeve. This is the same one on this slice over here, but this changes from this position to a position out here. So you are giving a much larger region a high dose. And this is something that can cause complications and that you want to avoid. So the correct way to do this is to keep the dose rate at point A constant, and to only change the dose rate and the doses out close to the region where dose is missing. And you do this by only increasing the dwell times near this position and leaving all the other dwell times, well, they'd be down here and in the tandem, leaving them as unchanged as possible, and try to keep this high dose range inside as unchanged as possible. And this you can do by changing only single dwell positions if you do it manually, or if you're doing it with a planning system, you can also use drag and drop of isodoses, but you must use it in a local way, which selects only dwell positions which are close to the place where you are dragging the isodose. Or a third possibility is what we will see later, is to use additional needles and place them out here in this region. So it is important to use point A as a reference position for the dose rate, and do this before you do further optimization, and then drag and drop the or change the isodoses, do a further optimization carefully, only with local dwell positions close to the affected area. Okay, and this is now shown here. You do this. You should do this for a standard loading. Use the same loading every time you use this applicator. You can do it either for equal dwell times on all positions, or after a geometrical optimization. And I will show you a little bit what that is in a few slides. And what we do is as a first step, as a first starting point, we produce an identical isodose or dose distribution for every use of this applicator, and use this as a starting point for the further optimization. And this procedure is intended to guide the optimization that we do later on, so that it keeps the high dose regions close to the sources, the hyperdose sleeve, so it keeps this comparable and in a magnitude which does not change the risk of complications. And we can see this because this kind of a shaping should deliver a similar track for for similar applications. Actually, this is a general rule in brachytherapy. In brachytherapy, we should always define a reference point for the dose rate, and we should always define it in a geometrical relation to the applicator. And that's in point for cervical applicators, this will be point A. But if we're doing, for instance, an interstitial application using the Paris system, our basal points, dose points, will be the reference point for the dose rate. Or in ICRU 58, you find recommendations to use a mean central dose, which is the mean of these dips between here at these positions. You can see it on here. Between these, where the dose rate rises this much, is where our dwell positions are, or our catheters are. And between the catheters, you will find a minimum. And the mean central dose is the average of these minimum positions here in two slices through the application. More of the definitions in ICRU 58. And this is actually the same system that you use in the Paris system, defining basal points between the sources and using the dose rate at these basal points as reference for the dose rate. And again, for equal applicators, this will lead to an equal or to an identical distribution of dose rates that are then locally adjusted. Okay, and then after you have done that, you relate the prescription dose to a position that provides the target coverage that you want. And this would be a point on a dose point on the target surface, or a set of dose points on the target surface, or for instance in the Paris system, this would be 85% of the basal dose rate that you have calculated. Okay, and again, a general rule is to only locally shape the dose distribution after you have done this. This is what you do when you perform a manual optimization. You may also want to use a mathematical optimization algorithm. If you do, you should try to use these rules in the constraints, or to transform these rules into the constraints, so that the constraints enforce this. What I mean is that you should, for instance, have a constraint that restricts high dose regions at places where you don't want them. And by this way, you can also lead the mathematical optimization algorithm to provide a dose distribution as you like it. Okay, a few words about geometrical optimization. I said you can use this as you can use this after you have or before you have set point A as reference point for the dose rate. What geometrical optimization does is it actually smoothes the dose distribution a bit. It adjusts the dwell times so that they compensate for dose coming from other dwell positions. I'll show you this in the next slide. It modulates the dwell positions that you see up here in this bar graph for different source positions. It would modulate them for a straight applicator like this here. All the red dots are source positions. It would modulate it in the way you see here. It would increase the dwell time at the end, and have lower dwell times in the middle. And what this in effect does is it straightens the isodose that is surrounding the catheter, so that if this is 100% here, so that this reference isodose reaches up to the end of the loading. Over here on the left side, you have the same catheter, but with equal dwell times, and you can just slightly see it here, that this reference isodose becomes more narrow here at the end, and does not give the same coverage as it does on the geometrical optimization. So this is one thing that geometrical optimization does. It improves the dose coverage, and you can see it better on these two parasystem breast implants on the lower slide. The left one is with equal dwell times, and the right one is with geometrical optimization. And this red isodose here is the 85% of the basal dose rate. No, this yellow line is the 85% of the basal dose rate, and this. No, not true. It's the red line is 85% of the basal dose rate, and this is what we would actually want to have as reference isodose, as prescription isodose. And you see that it does not cover the target as well out here in these outer positions. And the reason is the same as it is in this linear applicator. If we look at a dose position at the center here, it will be getting dose contributions from the right and from the left. And if we go to the outer positions, they only get them from the right. So they have less dose contributions from other sources. And that is why the dose decreases here. And it also decreases at the outer part of this implant here. And by raising the dwell times at the outer positions, we get this situation out over here. After a complete geometrical optimization, you get this situation that our reference isodose now surrounds the complete implant. And something we can't really see very well on this this image here, but what also happens is that these high dose regions, would be 125%, the blue lines, they become a little bit smaller. So the hyperdose sleeve becomes a little bit smaller. And in effect, so the geometrical optimization also homogenizes the dose distribution and reduces the high dose volumes between the sources. So this is an effect that actually improves the dose distribution for almost every applicator, and that we would normally do before we do any further optimization. So how does geometrical optimization work? This is very short. To understand this, I would recommend to read it in the references given here, or also given in the handouts, how it works. But what geometrical optimization does, if we want to optimize the dwell time at this position 2 here, what we do is we look at the dose contributions from all other dwell positions. In this case here, it's only dwell positions on the other catheter. There are also algorithms which do this on both catheters, on all catheters. And then we reduce the dwell time so that the dose rates, or dose rate coming from these other positions is compensated for. And this causes the smoothing effect that I just showed you on the parasystem implant, and reduces dwell times, and also reduces the high hyperdose sleeve around each of the dwell positions. This is actually normally a good measure to do, but you must do it with caution, and you should inspect the results of the geometrical optimization before you continue with planning and see what it does, because geometrical optimization can lead to unwanted shapes of the dose distribution. And this depends on the algorithm you're using. I told you there's some that use the dwell positions on all catheters. There are some that use them only on the other catheters and not on the same catheter that you are just optimizing. So it depends on the algorithm. It depends on the applicator geometry and on the loading. And these three little figures here show you different dose distributions that you can get by geometrical optimization for the same applicator, using different kinds of different algorithms, and also down here a slightly different loading. So you have to look which of these what your optimized dose distribution looks like, and decide if this is something you want to you want to continue with. Now I want to switch topics and speak more or explain a little bit more about the concepts of how target definition works. And I want to refer here to the JEC-ESTRO guidelines, which are about the same, given in the same way by the ABS or by ICRU 89, as you have just seen. This is these are the two publications by JEC-ESTRO that give you a good description of these things here. You've already seen these diagrams down here. I want to go into a little bit more detail of this. The JEC-ESTRO recommendations given in this work here by Pötter and no, it's given in this work here by IMED in the first set of recommendations. They define several different kinds of targets, as you have already heard, and these targets are doses which increase with the risk in these targets. The first thing, this Dr. Schwickert has already showed this. We have a gross tumor volume, which is the solid tumor as it is diagnosed, and the JEC-ESTRO recommends to diagnose this on MRI whenever you can. And this is diagnosed for some purposes at time of treatment. So this would be the residual GTV, and for some purposes it is diagnosed at time of first diagnosis, when the patient first presents and you see the full extent of the tumor that has developed in the patient. Okay, so we use this gross tumor volume, and it is always part of the high risk CTV clinical target volume that we define for our treatment. At time of treatment, we will define a high-risk clinical target volume, a high-risk CTV. This contains the gross tumor volume at time of treatment, and this should be based on MRI. It always includes the complete cervix and has no margins. Then we define an intermediate risk CTV, which includes the high risk CTV, the same one. So this here is our high risk CTV, and our intermediate risk CTV includes this. It's a black line. The high risk CTV plus a margin of 5 to 15 millimeters. The 15 millimeters are normally valid here in the lateral region towards the parametria, which one expects may be more infiltrated. And there are possibly no margins towards risks of organ like the rectum or the bladder. Another rule is that the intermediate risk CTV should always include the high risk CTV and the region that was covered by the GTV at time of diagnosis of the original GTV. So this gives us the intermediate risk CTV, and then the low risk CTV is the complete parametria and in extended disease at least, and is a region that we normally treat with external beam radiation in a larger region in the pelvis. So these targets are defined at every treatment for every fraction of brachytherapy on new images which were taken for this, which were taken recently before the brachytherapy session. And the segmentation, of course, and diagnosis of all of this is a task, of course, for the radiation oncologist. But as physicists, of course, we need to understand what this is. The different target volumes are treated with different doses, which increase with risk. And the risk is based on the assumption of the density of cancer cells in different regions. And this is shown in this diagram here. In the high-risk region, we will have a large density of cancer cells, and the density shown here by this line will decrease in the intermediate risk of target volume and decrease even more in the low-risk target volume. So we have less cancer cells or smaller cancer cell density in the intermediate risk and the low risk, and this also allows us to give us different lower doses in the intermediate and low risk target volume. So we have different targets with different different doses. Okay, this is just another slide you've already seen. This here would be the situation in a limited disease. And here you see that the target volumes are for extended disease. So these guidelines recommend that target definition should be based on MR imaging whenever this is available, and also treatment planning should be performed on MR images if you can, if you if you have enough access to an MRI. But it is also good practice to plan on CT and use a target segmentation that is achieved from MR diagnosis. That means that the radiation oncologist has looked at the MR, has seen where what the extension of the different targets is, and then transfers this onto the CT that you plan on. Then to evaluate the dose, what we use are dose volume histograms, and especially dose volume histogram metrics. And the slide here shows you what the dose volume histogram metrics are. For instance, the volume, the V100% is the volume covered by 100% of the prescription dose. V150 would be the volume covered by 150%. D90 would be the dose that covers 90% of the target volume. So these dose volume, and related to organs at risk, we have these other metrics like the D2cc or the D1cc or D.1 ccc. That is the dose covering 2 cubic centimeters of the organ at risk, or 0.1 centimeter of the cubic risks. This would be the hot spots, and maybe the 2 cc is a more representative dose for the risk organ. Or for larger parts of the risk organ. And these dose volume histogram metrics are actually only points on the dose volume histogram. And here you see the dose volume histogram for the GTV, for the high risk CTV, and for the intermediate risk CTV. And down here, the V90, for instance, or the volume that receives 90%, V90 is this point here on the tail of the dose volume histogram for the intermediate risk target. It's this point over here at 90% on the high risk, and this point here at, on the GTV. And these are points that you can use to prescribe your dose. You can prescribe your dose to 90% of the target volume by prescribing it to this D90% point that you find here on the tail. So it would be 70 gray for the intermediate risk, 87 gray for the high risk target. So prescription you can perform your prescription directly on these dose volume histogram metrics. Your planning system will normally allow you to do this, and this relates them to these points on the dose volume histogram. And for the risk organs here, it's the same thing. This here is the tail of the dose volume histograms, as shown over here. These are always cumulative dose volume histograms, and this here would be the 0.1 cubic centimeter points for the intermediate risk and the high risk, and this here would be the 1 cc points for the for the two targets, and this would be the 2 cc for intermediate risk and 2 cc for the high risk target. So these are numbers that your planning system will report to you. It will tell you these numbers, but you can actually find them yourselves by simply looking at the dose volume histograms and finding these points. Okay, and down here you've already seen this slice here too. This shows where these regions are for a case like this, and you can see that typically these hotspots, for instance, that are shown here are nested in each other, so that the 0.1 cc region is part of the 1 cc region, and is part of the 2 cc. That is part of the 2 cc region. So, and now the guidelines, and especially here, I believe Dr. Schwickert is going to tell more about this. We prescribe dose to these points defined by the dose volume metrics. These are the recommendations in the EMBRACE study, which is a large international study on cervical cancer, treatment of cervical cancer with brachytherapy. And here the doses that are recommended are more than 90 gray to D90 for the high risk CTV, 75 gray to D98 for the no. See, where am I here? No. No, it doesn't show it. It doesn't show the doses for the intermediate risk. Sorry, but these doses are prescribed first of all to the dose volumetrics, for instance, to D90, and they are prescribed as EQD2, that is as radiobiological doses equivalent to a fractionation of 2 gray, and for the targets, they are you use an alpha beta of 10 gray. And for the limiting doses for the organs at risk, like the D2CC, is also given as is also recommended as EQD2, but for an alpha beta of 3. So these doses in this table here would be the recommendations given in this study here, and you can find more about the study and its aims in this on this website given up here. All right, I think this is all of the school mastering that I wanted to show you, and I can now give back to Georg Schwickert. Thank you very much, and we'll answer questions at the end of the lecture, I guess.
Okay, thank you, Frank.
Thank you, sir. Dr. Diors, the platform is yours.
Thanks. I don't know if you see it also blinking. I just see it blinking here.
Yep.
Okay. Good. I just want to spend 1 minute again to the topic geometrical optimization, because it has been mentioned a few times now. And it's basically very simple algorithm. So you can do that more or less by hand calculation. So what is important is, if you have here, let's say you have source positions, the red points are source positions, you basically calculate from, let's say, position number 1, you calculate the distance to all other source positions, and you square this distance. And basically the dwell time is proportional to the sum of these distances. Here is the whole secret of geometrical optimization. And what you get is a kind of dwell time distribution that looks like this here. So it's purely based on the 3D coordinates of your source positions. And it's a relative dwell time distribution. It must be normalized to a point. Yeah, so that is has been invented many years ago by Craig Edmondson, and then it was put in the first nucleotron planning system in the NPS because they were a nucleotron user at that time. But it's a very simple, very effective algorithm. Good. Coming back to my presentation. I just want to spend a few minutes to show you some applicators. Of course, I showed you Varian applicators, but as I said, all vendors have similar applicators. So this is a basic cylinder that can be used as a vaginal cuff cylinder, but it can also be equipped with the intrauterine probes. This is titanium, this is plastic. So you can use this also as a cervix applicator, as a single channel cervix applicator. You can also use cylinders like this one here in combination with interstitial needles. And you can even combine this interstitial needles also with a template. So you have also needles that are parallel to your cylinder surface. Then you have the classical Manchester applicator that can also contain shielding segments in the ovoids to shield the dose to bladder and rectum. This is a Fletcher applicator with a fixed geometry where you have always 90 degrees between your intrauterine probe and the ovoids. And the ovoids are used closed always. You can, of course, use different sizes of the ovoids, but they are used closed, that no tissue goes in between to avoid too hot areas there. And these are the interstitial needles that you can use with this applicator. Similar applicator is this one. This is a flexible Fletcher applicator where you can tilt the intrauterine probe. And again, you can combine this with interstitial needles, and you have guiding tubes. So it's easier to insert the needle. And you see that you have needles that are more or less parallel to the intrauterine probe and needles that are angled 20 degrees. By the way, you use these plastic needles, and we have two different models of plastic needles. Blunt needles that have no sharp tip, and also sharp needles. And what we discussed also last week is this dead space. So the dead space is basically the solid part of a needle or an applicator where the source cannot go, but you see this on CT or MR images. So you need to know that the real channel ends here and that the sources can only be placed in this open channel, of course, and that you need to take that into account. I will show that when we switch to the planning system in a minute. Okay, and then we have ring applicators, different length of intrauterine probes. They have a stopper included, and you can combine these ring applicators also with needles. You just need to have a different type and a different cap that has needle holes, and then you can also create such an interstitial applicator. These are cervical sleeves, which you can use. They are put into the uterus and they are stitched on the cervix, so you don't need any additional anesthesia if you do a standard ring treatment. So you put the tandem into a cervical sleeve. You need, of course, to dilatate the cervical channel, but you do that only once. And for the next fractions, you don't need to do that because you have the sleeve in. So you don't need anesthesia for the second, third, fourth fraction, for example. And this is a very new type of applicator. It looks like a ring applicator, but basically it's the Aarhus ring template. It's basically not a ring channel, but a template, which means you are just using this with needles. And you can just simulate a ring if you place source positions at or in the plane of this template. Then you can simulate a ring channel also with this applicator. And of course, you use this also in combination with the intrauterine probe. Good. A very nice slide from Primož Petric, who is a doctor working now in Zurich. And he, at the time when he was in Ljubljana, he has pooled his patient target volumes. So I think these are about 250 patients. And he just overlaid all target volumes and got a kind of map here. So the grayscale or the intensity of the color indicates the, let's say, likelihood of the target area. So basically what he found out is he was looking for the best applicator that we can create. And what he basically found out is that if you use intracavitary treatment with a ring applicator without needles, you cover about 60 to 75% of all his target volumes of these patients. If you use interstitial needles in addition and parallel needles, then you can already cover 95% of all these target volumes. And you can just improve this for another 3% if you use also oblique needles. Now there's a small improvement, I would say. So with a ring applicator with straight needles, you cover already 95% of your patients. And 2%, he said 2% are out of this, let's say, applicator reachable area. So 2% cannot be covered even with oblique needles. Good. So let's go to brachyvision. Before I start with this, I just want to remind you the main important point in brachytherapy is this dose gradient. So we see we have this 1/r². We see the dose in a small area, and when we go out of this area, the dose falls rapidly down. This is very important to remember. So when I just do a theoretical example, this is the situation with the ring applicator, solid model of the ring applicator. I just assume a target volume of just 5 cc. This is my point A. I can nicely cover this with a pear-shaped isodose distribution. And it looks also, I just simulated bladder rectum, looks quite okay. We are close to these structures, but it's still acceptable. So if I do that as an example with 6 gray prescription dose, 2.8, and I use a 10 curie source, I need about 350 seconds of dwell time, total dwell time, yeah, in the tandem and in the ring to cover this. So if I go and increase the target volume only 1 cubic centimeter, 6 cc instead of 5, I have a situation that looks like this. So this is my standard plan, 350 seconds total time, and it looks like this, and part of my target is not covered by my isodose line. So if I want to cover that, and I blow up my dose distribution so that it covers this area, then I need 462 seconds, which is an increase of 32% of the total dwell time. And you see what happens. Of course, I violate my restrictions to the risk organs. So it's not a good idea to just blow up your dose distribution. If you use just 1 needle with 3 source positions, you can nicely shape your isodose line around this 6 cc tumor volume. It looks still good, for bladder and rectum. You see here I can cover the whole theoretical tumor volume. And I need a treatment time, which is only 4% more than so I added only 4% time in the needle to get a good coverage. And you see that the needle is even not centered in my target volume. So what I want to say basically is with a small additional dwell time in interstitial needles, you can dramatically change your dose distribution. And you don't need necessarily to increase your time. Good, this is something that I want to show later. I'm now switching to planning system. So this is my brachyvision planning system running on my PC here. So I'm just going to open the planning module here, and I just load one example data set. So this is my image set, MR based. So what we see is that it has already been contoured. So we see actually here a GTV, we see the high risk CTV, we see an intermediate risk CTV, bladder, rectum, sigmoid. So if I activate the structures, we can all see the structures. This is a T2 weighted MRI image. Yeah, this is let's say for the doctor, the primary image where they contour the target and organ at risk. For the physicist who has to define the applicator, it might be not the best choice, because if we look where we see the applicator, and I just deactivate the contours for a minute, okay, we can see the applicator. If I go, let's say, in the center of the intrauterine probe, we see actually here is the uterus. And if I go to the frontal image, yeah, we see here is an applicator, we see the uterus, we see the ring channel. Points have already been defined. Yeah, there is an ICRU bladder point and there is an ICRU rectum point. We will see that later, how that looks with the plan. So let's use this first to insert a new plan. So I insert a new plan. That's my course 1. My target volume is a high-risk CTV. I just need to check this, and it will also create a reference point. And then let's name this intracavitary plan. And what I need to specify is the technique. This is something that is specific to brachyvision. We need to just name this as intracavitary technique. And we specify the percentage of dose and the absolute dose. Let's plan for 7 gray total dose or prescription dose in 1 fraction. That's fine. So I create a plan. So as I said, this applicator is not so easy to define here. So, but in this case, we have registered images. So I have also a T1 weighted image or image set. And I can actually blend over from one image set to the other. So it's already registered. This is a T2 weighted. This is T1 weighted. And you clearly see for the T1 weighted images, it seems to be much easier to identify the applicator. Look here, it's nicely visible. Okay, so I'm using this. I'll just rotate my patient a little bit so that I'm really looking in the center of my tandem. And then I save this as the default viewing plane. It saves just the orientation and the magnification of this. Good. So we need to have the applicator inserted. So I can do that by inserting a solid applicator. It's named a solid applicator because it's a fixed geometry. And we have a library for these applicators with a fixed geometry. And we just need to select the correct applicator. This is a ring applicator, as I said. So there is a long list of applicators, but we just are looking for a ring applicator. Actually, it's an interstitial ring. So I can just filter the list. If I just type something in and then it's filtering the list automatically. This is a tandem of 6 centimeter length. You see here representation. I add this to my plan. And we have a ring cap that has also needle holes because actually it's an interstitial plan, but I want to first develop an intracavitary plan and then I show you the difference when we add needles and how we do that. So let's add these 2 channels into our target. I just need to select a treatment machine. Let's say I have a Browse afterloader. Okay, because I made a mistake here, I did not click on the transverse image, therefore the applicator is coming in a wrong direction, but that is not a problem for me. I can just rotate my applicator so that it is in the correct orientation. And I can move the applicator. So what I want to do is, of course, I want to bring the applicator exactly at the position where I see the applicator on the image. Good, let's go to the ring plane and also look at the transverse plane if the applicator is correctly placed. Yeah, maybe we could shift it a little bit to the right side here. Yeah, but basically it seems to fit. So this is also the advantage if I use a solid applicator model, that we don't need to digitize the applicator and the geometry is already correctly defined. I mean, there might be a slight modification here that I need to rotate it slightly to the right side because I see here the channel coming in, but basically it should be okay to have it like this. Good, if my applicator is placed, I need source positions inside the channels. I can load the source positions graphically. I just need to activate a tool and say, okay, I want to have source positions in this area here for the tandem. And then it will put the source positions with a standard step size of 5 millimeter. And the same for the ring. I can just say, okay, I want to have the source positions inside the ring, and I want to use the whole ring. And then you see source positions are also placed in the ring channel. On the left-hand side, you see the applicator, you see the intrauterine tandem, you see the ring probe. And you see that these applicators are grouped, which means it's just one applicator model, but it's 2 channels, which means when I move something, they move together. If I right-click, I could ungroup them and can only move the ring or the tandem, but normally this applicator is geometrically fixed. Of course, there is always a possibility that something is tilted and need to be adjusted, and you can use this functionality. Okay, so we have no point A, point B, so I will quickly define this. Remember, we go into the center of the intrauterine probe. We can maximize the frontal view, and we see nicely the cap of our applicator. So we can measure from here 2 centimeter. And that's what I'm going to do. So I insert a new reference point. And it makes sense to use a circle cursor in this case, because this is a circle cursor that I can adjust with a radius. If I use a radius of 2 centimeters, it becomes very easy for me to measure, because now I can measure from the intrauterine channel, from the center, actually, and I can measure from the cap. If I click here, this is point A, and that is left patient side. We'll keep it as a risk point. It doesn't matter, basically, it's just an indication here. The same way we can insert another reference point on the other side, on the right side of the patient. We're just going to do that as good as I can. So this is point A, right patient side. Okay. So if I blend back to MR2 weighted, we see both points. And we can also place point B if we want. You know, this is 3 centimeters away from point A, the same level. So if I go here at the level of my A points, I could do the same again. So I insert new reference point and location, but now I use a radius of 3 centimeters. So I see the plane, I see where I need to go. 3 centimeters away from point A is 5 centimeters away from the intrauterine probe. So point B left. So not really difficult to do that. Good, and we double check that we are in the plane of the tandem with our point A and point B definition. Good, so that looks all quite good. We just need some dose. So we need some time in the 12 times or in the 12 positions. So there's one possibility. The simplest possibility, I set the 12 time manually. Yeah, for example, I could start with a time of, I don't know, 15 seconds for always for 10 Curie source. So the activity here in the planning system is always 10 Curie. So if I set this, we get a dose distribution, which is not normalized to point A yet, which can easily be done. So I can go normalize to a reference point and choose maybe my point A on the right side. So I get 7 gray exactly on this point. And it has a pear-shaped dose. So actually something that we could start with. So let's look at our tumor volume. Okay, we see already if we just activate the high-risk CTB. And let me go to the T1. That's easier to see for you. So then you see the high-risk CTB is extending to the left patient side. And this is not covered by my plan here. Okay, let's try to improve this situation. We can also look, of course, at the 3D representation here. Just activate the prescription dose. So we see the applicator here. And if I would switch here to my T2 base planning, you see also the target. I could copy these targets into the other data set, so the structures, but I just keep it like it is, like this here. And look at my 12 control window. So we have tandem and we have ring. And here you see the positions and the times. And because we have always the same time, I'm just looking, let me just look at the 10 Curie time. So if we look at the time, all positions have the same time. Do we need all the same time? I mean, this is times of radium, where we use radium, but we have a stepping source. We can utilize the stepping source. So we can have different 12 times at different positions. So we have talked about this geometrical optimization. Let's do a geometrical optimization instead. So I go to geometrical optimization, and now I can normalize this. It needs a normalization point. Let's say point A, right? So we have also a nice dose distribution as a starting point. But what you see now is that what I showed before, outer 12 positions get more time than inner 12 positions. And that is also the same for the ring. The outer positions get more time than the inner positions because they have a greater distance to all the other positions. And they have no neighbor on the other side. So is that what we want? We look at, let's say, the bladder and the rectum. Okay, so that doesn't look nice here on the sagittal view because we get a quite high bladder dose. So we would need to modify this now. We can look at the tandem, and you see if I hover the mouse over the positions, you will see that the source position is highlighted in red color. So I know where I can manipulate my time manually. So for example, this area here, where we get high bladder dose, corresponds to the source positions. So if I reduce the dose or set it to 0 in this area, I can shape the dose. Yeah, you can see that. Let's take another position. So we are shaping the dose. And the other contribution for the bladder comes probably more from the ring. So I can also go here in the ring, moving my plane in the ring so that I see this in a transverse plane. And here I can also hover my mouse in the ring channel and see where I am close to the bladder. So I'm just going to manually change the dose there just to see the effect. Rectum, the same. So I can look at the source positions which are here located. Let's go here, down, down, down. Yeah, it's a bit slow. But anyway, so it's somewhere in this area where I can reduce the dose to get less dose to the rectum. So I can shape the dose this way, just manually. Looks a bit strange now, that dose distribution. And of course, I don't get the point A dose that I want. If I look at the point A dose now, it's 4.5 gray, but not 7. I could renormalize. So I go again and normalize to my reference point and specify 7 gray again. It will blow up the dose distribution, but it is better than it was before because I shaped the dose already. So I get not this high bladder dose anymore that I had before. Probably it's still too much, but you see that I can nicely use these tools to shape the dose. Or I activate this graphical dose shaper, which could be adjusted to a more global effect or a more local effect. If I just want to change individual 12 positions, I would more go to the local effect. And then what happens if you look at the sagittal view here, I can just drag my isodose lines. And what you see, what happens here is that it will change the, of course, the 12 times. When I drag the dose, it will change the 12 times. Good. Let's say, okay, this is our standard plan. So we have reduced the dose to the rectum, to the bladder. You see the shape here in the transverse view. And we still can maintain point A dose, more or less. Yeah. I just reduced it now a little bit to 6.7 gray, but it will not greatly affect the dose if I renormalize again to point A. Good. This would be a standard plan. If we look at the 3D representation here, we still see that it does not cover a big part of my high-risk CTV. But that's the best I can do with my 2 channels. So if we look at the report, we have a total treatment time for this example of about 500 seconds. Just keep this in mind, 499 seconds. That's my total time. If I multiply this with the activity of 10 curie, I come to my track. So this is the total air Kerma strength here. That's multiplication of the dwell time and the activity. And you see this also here in curie seconds, which is just a multiplication of 10 curie times 499 seconds. So this is a, let's say, parameter that gives me an idea about how much dose I deliver into the volume. Good, let's keep this as a intracavitary plan. Now I copy this plan, paste the plan into the same image set, and now we want to develop an intracavitary and interstitial plan. We keep the dose the same. I did not change anything yet. It's the same dose distribution that we just developed. But now we look again at the T1 weighted image, and I just deactivate the dose for a moment, and maybe also the visibility of the applicators, because I just want to concentrate first on the needles. You see there are needles here, 1, 2, 3, 4, 5, 6 needles. And we want to introduce these needles into this plan. So I go insert new applicator. And I name, let's say, the first one, needle number 1. And you see the dead space parameter here. And this plastic needle has about 4 millimeter dead space. Let's type this in here. Good. How to identify the needle. This is not quite easy. It's a bit tricky, and you need some more information about this needle type, and you would also need a kind of commissioning of the needles to find out where is really the tip of the needle. So we assume that it's not important for the demonstration now, but we assume that the tip, you will, if you do a commissioning, you will see that if you use titanium needles, you get a broad signal at the tip of the needle because of the solid applicator or solid needle. So, but it's basically somewhere here, maybe a little bit lower. And I define a second point here. So this could be the first needle. I rotate my patient a bit so that I can also see the needle in another plane. And here you would see, or you see that I could correct this slightly. Okay, where's my target? That's my target. So I look at the needle again and the target, maybe. And then I define the source positions. I cannot put in source position up here, but at least I can put them somewhere in here so that I have enough source positions inside my high-risk CTV. Good. Now I'm just using a method of copy and paste to create the other needles because that's the quickest way to do that. So I can just copy an applicator and then I'll press Control V, and then I create another needle number 2 and needle number 3 and needle number 4, 5, 6. And then I can move the needles first to the positions where I see them. So that is needle number 2. And we will adjust this, of course, in a minute so that the positions are correct. Just roughly, I move the needles where I see them. Needle number 6 is here, over here. Good, because I copied them, they have the same source positions, but we can also change that if this is required. So now let's look at needle number 2. There is a nice tool. I can just right-click and ask, move the viewing planes to the tip of this needle, and then I'll deactivate the other needles because otherwise you're getting confused. So this is actually the other needle. The tip is here. I modify this position slightly. I'll look in the other plane. That looks quite good. And I go to the next needle. This is probably a little bit more up here. Again, I can always rotate my home data set to look into the needle itself here. And then I see that it quite nicely fits with my images. And I can already go to the next needle and move also the viewing planes to the tip and activate this contour editor to place the needle where I see the tip. And check this and the sagittal view. This is a little bit tilted. Two other needles to go. So here's the tip a little bit lower. That looks good. So let's look in the other plane. Needs a bit of tilt in this direction. And needle number 6. So you see already it's not too difficult to do that. It's another question, of course, for the doctor to get the experience to place the needles. But from a planning perspective, it's not too difficult to do that. Okay, so we have all needles defined. We can look at the situation again if I blend over to the T1 weighted images, so and to the T2 weighted images, so we can see the whole situation here. Let me just activate high-risk CTV, and then we'll see how the needles are placed here. Okay, we still have a dose distribution. And I can activate that again. This is the dose distribution that we developed for the intracavitary plan. We don't use any needles yet. They have all 12 times 0. We did not specify anything here. So we are still looking at a dose distribution coming only from tandem and ring applicator. I just move the planes in the center, so it's easier to evaluate the dose, and I minimize that a little bit. So if we just look at the dose distribution here, and we go, let's say, in the biggest extension of my high-risk CTV, we see that's here, we have the needles here. So I should be able now to cover this area. So how can we do that? Again, we can use the dose shaper, or we can go to the 12 control window. And we will see that we have now needles here that have no dwell time. So as a first approach, I could think, okay, let's lock the dwell times in the other channels. So I lock the time in the tandem, and I lock the time in the ring channel, because we want just to manipulate now the dwell times in the needles. This is possible here in the planning system, that you can lock dwell times. And then if I look here at needle number 1, needle number 2, this is the area where I need some dose. Maybe not so much from needle number 1, but more from needle number 2 here. So let's start with this. So I go to needle number 2, and I just add some time manually. You see the effect? It's enormous. A few seconds dwell time, how this shapes the dose here. And to do it with a dose shaper, we can do that the same way. So in this case, I would go a little bit more for global, because we want to change more than just one 12 position. And then I can go just here and just shape my dose, so that let me deactivate the other isodose lines. We just want to see the, let's say, the 7 gray, then it's easier to see also the target. So if I do that, you see that I can graphically just cover my high-risk CTV. Of course, this is not the end solution here, but just to see how easy it is to manipulate this. And what you also see, that we have very, very small, just looking at, again, at the nominal dwell time, very small time contributions in the needles. Actually, there is a recommendation from the Astro that you should not get more than 10 to 20% of the total dwell time in your needles. So you should not deviate too much from the classical Manchester system, basically. So, but if I look at this, let me just quickly close this window here. So that looks, from the coverage, it looks not so bad. If I activate my bladder dose now and the rectum, the structures, then I see, oh, there might be still too much dose to my risk organs, and I need to modify that. Actually, when we do that, we can also look at the surface dose, which is quite nice. So if I look at the surface dose of bladder and rectum, and maybe also my high-risk CTV, and then I specify the maximum dose to, let's say, 10 gray. So I see the situation here. What is the dose that I deliver to my target, and what is the dose that I deliver to my risk organs? And you still see that we here at the bladder, we have probably too much dose. It's a hot area. We see this, it's a real hot spot. So we need to modify the plan still. And you can see that here clearly. So, but if I want to modify that, then it's not sufficient to keep the standard dose or the standard time in my ring channel and in my tandem. This is not sufficient. We need also to modify the dose there. So that means I need to unlock this 12 times here in the ring and tandem, because otherwise I cannot achieve my goal. If I do that and shape the dose just in the satchel view, I use my dose shaper again. You see how I can influence the dose so that we get less, oops, that was my fault, so that we get less dose to the bladder. Okay, regarding point A, point A left, point A right. Point A left doesn't have any meaning at the moment. You see we have 15 gray here. It's in the middle of our target. Point A right might be of interest for us. We have 6.4. Let's normalize again the dose to this reference point. So we blow up a little bit. And then, of course, you see we could still shape the dose more. So I would do a dose shaping like this, and maybe at the end I would normalize again to my point A on the right side of the patient, and then check if we can still cover our target. Close that for a moment. Okay, that's the dose distribution. Of course, you can always click here on DVH and you can evaluate your structures, bladder, rectum, high-risk CTV. It might be already a good solution. Just quickly looking at the report, what does it say? Okay, I get 565, so I get more time, definitely more time than I had before. Before it was about 500, but I have a much better coverage. But now I can also specify what is my goal. So I can specify clinical goals. There's a possibility here to add and edit clinical goals. So I say most important for me is the high-risk CTV. What is my objective? My objective is that the volume that gets 100% of the dose should be at least, let's say, 98% of the structure volume. So I want to have 98% of the structure volume covered by 100% of the dose. And the variation, what is the variation that I allow? Let's say if I get more than 95%, I would be also happy. I do two other structures here.
Sir, we have time constraint. Kindly try to finish your lecture on just time.
Yeah, no problem.
Thank you, sir.
So we get rectum and bladder. So we are specifying D2cc as recommended. Should be lower than, let's say, for the bladder 80%. And let's say I would be happy if it's 85. And specify for the rectum something similar, D2cc less than 70%. Rectum is a little bit more sensitive. And I would be happy if it's less than 75%. So these are clinical goals. So if I look at my clinical goals and I enter this, I see here that one of my clinical goals failed. I have too much bladder dose. The coverage is quite okay. Rectum is good. So now we'll try and modify the dose with an inverse plan or inverse planning. So I use my clinical goals now. I add this to my optimizer and use this clinical goals to optimize the times. So I don't adjust anything else, but I just optimize here to do it quickly. The optimization is completed. The system tells me, I say, okay, and just take it as it is. You see that the clinical goals are already fulfilled. So the system has changed the 12 times that I fulfill this clinical goals. It has changed the isodose so that I can fulfill also the bladder dose. I'm just looking quickly to the total time. Total time is now less than with the standard plan. It was 500 or 499. Now we have a little bit less than this. Last step I show you here is I want to evaluate this dose distribution. and I want to evaluate the interstitial plan compared with the intracavitary plan. So I look at both plans and I evaluate both plans with my clinical goals. I see here the huge difference. This with a triangle is my optimized plan, my interstitial plan. The other one is the standard plan. So it's much better in dose coverage, which you can see here. This is the intracavitary interstitial plan, and this is the standard plan. So less dwell time, less dose delivered in the volume, but much better local coverage of my structures. Good. Coming back, I still have maybe 2-3 minutes. I want to show you something about applicator commissioning. Just that you see the problem. This is a ring applicator, and you see the wire, the active wire, and I going now and retract the wire. And what you see is the purple position is the tip of the wire. Here's the source. But this is what the planning system is thinking where the source is. So there's quite a deviation. And this is, all vendors are affected by this because it's dependent on the tension of the wire inside the ring channel. And this changes, the strength changes, the tension changes, and you can never get exactly the same position as in the planning system. But you can modify your plan. And to do so, you would need a commissioning. You would need to do commissioning of your ring applicator. That means you use a galvanochromic film, you put the ring onto a galvanochromic film, and you take autoradiographs. And then you define where is the real position. These are the black dots. This is with unequal positions, and these are equal positions. So you cannot go 5 millimeter steps because then you cannot separate the spots anymore. So you need 1 centimeter distance, and therefore have one with an offset of 5 millimeter and the other one without offset. But this is the resulting situation. You can now modify your plan in brachyvision that you pull the planning positions to these positions where you have your spots. Yeah, that is actually, it's shown in a small video how to do that. If we are running out of time, I don't want to spend too much time with this, but you see these here are the planning positions, the purple ones, and you see under these positions, you see the spots of your autoradiograph. And what you can do now is you can create a plan, and you can modify the positions, your planning positions, that they fit to the measured positions. And with this, you just create, let's say, a standard plan. And if you create a standard plan like this, then you can modify the standard plan for each patient. Just 1 minute, you see how this is done, how we change these positions. So you have actually the channel, and you can now move channel points. So I want to move this first position here. And you see what happens? I overlay the 12 position from the planning system with my spots that are measured with the autoradiograph. And if you do that for all these positions, I can skip that. In principle, I think you understood how that works. Then you can save this as a standard plan. Last 3 slides. Dose summation. Always a question, can we add brachy dose to external beam dose? Yes, you can, of course. All vendors offer this possibility. But if you do rigid registration, you see that the external beam structure. Here you see the uterus and the brachyuterus, they don't match because with the applicator you probably have moved the uterus. If you do rigid registration, this doesn't work. If you do elastic deformation, it could work, but it might be also not perfect. But if you do a registration, which is a deformable registration guided by the organ and by the applicator, so this is shown here, then you see that we can match external beam and brachytherapy anatomical structures. And then, of course, if we do a biological weighting of our doses, which has been shown before, EQD2, then we can add the dose and can sum it up. Now, this is, let's say, advanced technique to do that, but in principle, this is possible. And that is, again, the same that Frank Hensley has shown already. These are the planning aims related to total dose and related to EQD2, alpha beta for the target of 10, alpha beta for the risk organ of 3. And that is what the EMBRACE study recommends. Good, that was my last slide. Thank you for your attention. So I think we would be ready now for questions.
Thank you so much, sir. Thank you for your informative lecture. It's time for the question. We have received some question. So my first question is from Manvi Dikrit. She wants to know about HRCTV, IRCTV on CT image.
Yeah, in principle, it's of course also possible, but it's let's say your target organ is difficult to delineate on CT. The organs at risk, if you contour bladder rectum, that is basically easy to do, let's say, but to really identify the high-risk CTB is not easy. I mean, if you don't have other possibilities, it might be possible, related also to your clinical examination, but it's definitely easier with MRI.
Yes, it's the target is simply not visible on CT, or can be invisible on CT, but you can see it on MR. That is why the recommendation is always to look at MR if you have it. If not, you have to use other information like clinical inspection and clinical diagnosis and things like that. But the gold standard, so to say, is using an MR. That's the recommendation. And if you don't have a planning MR, what you can do is you can get the information where the target is from the MR images, and then put the same shape or the same anatomical position of the target onto your CT.
Okay, it's really very informative. And the second one from Asad Yusuf. Why we're keeping jaws superiorly as there are no volume at tip of tendon?
Why we are keeping dose superiorly as there is no volume at the tip of the tendon? Yeah, that's a good point. I mean, you can, of course, you can reduce this dose there, but keep in mind that the low risk CTV includes the whole uterus. So we need to make sure also that there is, and historically, it was always loaded up to the tip of the tendon. So therefore, I think the tendency goes in this direction because you can spare risk organs if you don't treat up to the tip of the tendon. But this is really case dependent, I would say. and you would need to discuss that definitely with your doctor.
Mhm.
Thank you so much, sir. I want to extend my warmest thanks to both of you for sparing your valuable time and knowledge with us. Thanks to all the participants for their active participation in the program. I would also like to thank Dr. Abu Zakaria, founder chairman of SCMPCR, and the entire team of SCMPCR, whose tireless efforts have made this platform functional for us. Before the ending, I remind you again, we have changed the schedule of the lecture 8, Brachytherapy QA and Safety on 20th February, and group discussion on 21st February. The lecture will be held at 10 a.m. to 11 a.m. Thank you everyone once again. We appreciate your presence here. We will see you next lecture.
Thank you.
Mhm.
Our next
Thank you all.
is on brachytherapy QA and safety. Okay, I pick a question from the chat box. This question is from Suresh Padel. His question is, if the ovaries are placed unsymmetrical with respect to tandem in Manchester system, what shall we do for evolution of those 2 points?
Okay, good question. Keep in mind, if your ovoids are not symmetric, what we don't want is to have point A in the high dose region. So you can always, let's say, specify point A from the cervical os. So we use the level of the cervical os, specify this 2 centimeter lateral, 2 centimeter cranial. So even if the ovoids are not symmetric, we want to keep the point A at an area where the dose lines are going more or less parallel to the tandem. We don't want to have point A in an area where we have the high dose gradient, so too close to the ovoids. So if these ovoids are not symmetrically, I would recommend keep point A at the level or measure from the level of the cervical os and keep it there. Don't move it with a let's say unsymmetric ovoid shape.
Thank you, sir. Your excellent teaching skill and knowledgeable lecture has helped all the participants to learn. Thank you everyone once again. We appreciate your presence here. We will see you on next lecture. Okay, now I announce the end of today's lecture. Thank you all once again and see you on tomorrow.
Thank you.
Thank you. Have a good night.
Yes, good night to all. Thank you all.
Thank you, sir, and thank you all. We will